Hello, this is Stoichiometry section 9.3 where we look at real-life chemistry and actually how it could relate to your everyday life. So some important vocab: limiting reactant means that's the one that's going to run out first. Excess reactant is any reactant that is left over once that limiting reactant has been used up entirely. Percent yield is the amount that you actually did make from what you actually should have made, on a paper calculation. So it's going to be less than what you actually could make according to your calculations. Molar mass is familiar. Theoretical yield is what you make on paper when you're doing your calculations. Actual yield is what you actually make when you do any kind of experiment. So make sure you answer these intro questions before continuing. They're meant to guide you and get you totally into it. Alright, so limiting reactant is something runs out. Just like when we have a sandwich, we're making things, they obviously come in different packages, different sizes, different recipes for sandwiches, so to speak. Like this person likes 3 pieces of lunch meat and 1 slice of cheese. I'm more of a cheese man. I might change it up. You probably have something else you like doing. Well, if you have given amounts, given numbers of your reactants, you're going to make some of your products, but you're going to have excess left over too. This is what normally happens in real life because in chemistry we can't do everything to the molecule or to the formula unit or atom. It has to be by grams and moles, but there's going to be some left over, and obviously when we have something like combustion with something burning with oxygen, oxygen in our atmosphere is the limiting reactant, and we have the fuel that will run out first. So what makes this different in chemistry is we don't count up the number of molecules we're using, we use masses. However, we have in previous chapters gone from mass to moles. So that's the step that we're going to be looking at. So these are some general steps to determining the limiting reactant. You first need to see what's going to minimize your amount of your product. So if you started off with a given amount of one of your reactants, and then a given amount of your other reactant, and converted it to the same product. You see this is a product over here. Which one limits your amount of product? Just like the other side, which one limits your amount of sandwiches? So whichever produces the least is your limiting reactant, and that's key because that's the number or value you're going to use to do any other calculations after that, because your products are based solely on the fact that that runs out first. So we see NaOH runs out and produces the least. And it doesn't matter what the initial number is. You see there's 15.2 compared to 9.68 because they have different ratios. There's a lot of different things going on, so you're not going to be able to just look at it and know. So let's see an example for ourselves. In making methanol, you have carbon monoxide and hydrogen make methanol. Now if I have so many grams of each, which are both gases, which is the limiting reactant? So for each of these, I'm going to need to do 2 conversions using my chemical equation. Now again, chemical equations are going to be balanced, so we don't need to worry about that. But I'm going from my 325 grams of carbon monoxide and my 600 grams of H2. Labeling is key. Now when I'm trying to compare, I only need to go to moles of methanol. Because if I went to grams, all I'd be doing is multiplying both values by the molar mass, which again would be the same comparison. So I don't need to go more than to moles to see which one's my limiting reactant. So, like usual, what's on top goes on the bottom, grams of carbon monoxide. I know grams are always related to moles of carbon monoxide. And again, that's not what I'm trying to find. So moles of carbon monoxide need to go on the bottom because that's what's on top. And when I'm in moles, I can relate that to a different substance like we learned in the last section, which in this case is methanol. I will be checking to make sure that you are labeling, and it will be required for on the test. I look at the coefficients in front. In this case, they're both 1. 1 mole is so many grams, so I have to calculate my molar mass, 28.01. Again, 2 decimal places, like money. And I'll go back and look at the calculation for that in a moment. Down here, again, same procedure, just with a different chemical. But again, I need to compare it to what I have for each. Now again, this one has change my colors here, 2 moles for every 1 of the methanol. And of course, this would have a different molar mass because it's a different compound. So let's see what these are in comparison. So, my moles of methanol from my carbon monoxide would be 11.6 moles. While for my hydrogen, I'd produce 297 moles. So think about it. Which one limits your amount of product? Hopefully you identified carbon monoxide as our limiting reactant, which means our excess reactant is hydrogen. Now that we know that carbon monoxide is my limiting reactant, that's the value, the initial beginning of what I'm going to use to go forward. So let's take the next part of this. Considering I didn't use all of the excess reactant, how much would be left over? This is a key feature because hydrogen is a very flammable explosive gas, and if I have a lot left over, I'm going to want to deal with that. And I'd rather deal with that on paper first before I deal with it in real life. However, like we said, we're going to want to use our 325 grams of carbon monoxide. So 325 grams of carbon monoxide is what we know we use entirely. I want to find out how many grams of H2 get used if all of that carbon monoxide gets used. So this is a grams to grams. This is section 9.2. So grams of carbon monoxide to moles of carbon monoxide, and then moles of CO to moles of H2. Again, this is our 1 mole ratio that we can convert using our chemical equation to go from one substance to another. And mole of H2 to grams of H2. And then I just fill in my molar masses. My ratio from my equation, which I believe is 2 to 1, and then 1 mole, 28.01 grams. 20.01, yes. So I see that I have used 46.9 grams of H2 in using up all of my carbon monoxide. But that's not the question. The question, careful reading, would see how much would be left over. So I started off with 600 grams of H2, again decimal, minus my 46.9 grams. That's a G, by the way. So my common decimal place would be to the ones place. So 600 minus 46.9, I get 553.1 grams remaining. So that's 553 grams of H2 unused, or left over, however you want to talk about it. Okay? So that's how much would be left over and not used. Now I'm going to erase this so I can work on the methanol here. Have some more space here. And again, go back if you needed to write that again. So how many grams of my product? This is again back to straight stoichiometry. I have so many grams of my initial part, and you always start with that number. Don't start with moles or whatever you calculated before. Yes, do the long method. It prevents rounding. We should all get the same answer. If not, you'll lose points because you can be correct, but taking shortcuts is not an approved method. So again, molar mass, moles of CO to moles of our methanol times our molar mass of that. So we have our 28.01 from our previous math. I think it was a 1-to-1 ratio, yep. And then methanol is our 32.05. Adding everything up. So my amount made here, so multiply all your numbers across the top, divide by each number on the bottom individually. That'll play a bigger role when your coefficient on the bottom is a different value. So, but aside from 1, so 3 significant figures, 372 grams of methanol are produced. So let's take a look at percent yield. The calculation or the equation is actually up here and got transferred in the process. But this is sometimes an indication of how well the experiment was performed. Just like when you think that you're making cookies at home and it says makes 24 2-inch cookies. Well, I don't know how well you are making 2-inch cookies, but sometimes when it says 24, I might make 22. And so the percent yield would be what I actually did, 22, over what I should have gotten, 24, and so my percent yield is a little bit less. This often happens in normal practice, and when we do labs, you see that there's always some error, so that you will get less than 100% yield. The higher the better, of course, but some things, like a lot of pharmaceuticals, have a very low percent yield just based off the chemistry itself. So let's take a look at how we can use this in our everyday part when dealing with labs. So we have the same equation as before. You would have your normal stoichiometry to do and calculate your theoretical yield. You're always going to use this to calculate your theoretical yield if provided some of the initial reactant. Then you use the equation to put in what you actually got in the experiment. So you have an experiment, you compare that to what you should have gotten in theory if everything worked out perfectly. On some occasion, you might need to find the actual yield and you're given a percentage. We will be doing this in our lab to where you're going to try to determine what was actually there or theoretically there in order to see what contaminant some soil had. So looking at this example, I have 75 grams of carbon monoxide producing so much of the product. Students will often look at this and think it's a limiting reactant problem. However, what you should notice is the fact that this is a reactant and this is a product. So it's already telling you that this reacts to produce it. So this is your actual yield for your product. But we need to see what's my theoretical yield. Theoretical yield from my given reactant. So we need to just calculate that doing some simple stoichiometry. So 75.0 grams of my carbon monoxide, and I need to know again how many grams of my methanol am I going to need to, or am I going to produce in theory. So grams of CO to mole of CO. Again, we have our mole ratio to go from one substance to another, and again, you should really take note, I'm working from bottom up with every conversion. It's never top down. If you find yourself up on the top, you're making it harder than it needs to be and not giving yourself those visual cues in order to get there simply. So I just happen to use some of the same values from before because you should be able to calculate any molar mass. That's not really the question that we're trying to solve here. It's a 0, by the way. I believe it's a 1-to-1 mole ratio, yep. And in this case, 1 and 28.01. So in theory, I should have gotten 85.8 grams of methanol as in my theoretical yield. So I had actually 68.4 grams of methanol over my theoretical times 100%, because of course we want this as a percentage. I see I have 3 sig figs for both, so that gives me 79.7%. That might be alright, considering we're dealing with some gases. Let's just take a quick look to see how it would look if I gave you a percent and you had to determine an actual yield. So I'm going to take this same percent that I have here. Actually, I'm going to change that percent. I'm going to change that percent to determine that I'm going to get a different actual yield here. So let's look and say if I had the same equation and I had an 83.0% yield, and I need to know what is the actual yield of this same concept here. So again, actual over theoretical times 100% equals percent yield. So if I substitute my values in, 85.0%, my actual is what I'm trying to find, that's my variable. My theoretical I had here at 85.8 grams, and then I have my times 100%. So we're solving for the one variable here. This is something you should be able to do, being proficient in algebra, and we're going to continue on doing that throughout the next couple weeks with gas laws. So divide by 100%, both sides. So that gets rid of that. And then this becomes 0.85 is equal to A over 85.8. And so if I just get that value, 0.85 times 85.8, because you want to multiply both sides by that value, because when you do it on this side, these will cancel out, leaving you with your actual yield. And I see I dropped my 0 here. So I should have 3 significant figures, in which I get 72.9 grams is my actual yield. So this just goes back to algebra, making sure you just do all the steps, order of operations, and so on. And that's it.